gonna go.
Yeah.
All right. So last time we were in here, we were drawing slope fields. Today we're doing the reverse. They're giving us a bunch of slope fields, and we are matching them with their differential equations. So we're going to go through a few examples that's in your packet, and then you'll finish up the rest on your own. So this is number 2 on the front page. They have given us 6 differential equations. They have given us 6 slope fields. So we want to match each differential equation with its slope field. So, thoughts on that? What do you guys see?
C is the first one.
C is the first one. Why do you say C is the first one?
Hills and valleys.
There's hills and valleys.
It's the only thing with a trig function.
It's the only thing that looks like a trig function. All right, so I'll go with that. So C is that.
Is that right?
That is correct.
Oh, sweet.
What else?
The second one could be A.
The second one could be A. Why do you say that?
It looks like parabola.
Looks like parabola.
Oh, wait, no, because wouldn't that be x squared, not y squared? I don't know.
Then remember, we're looking at the differential equation, and we're looking at the slope field. What is the slope field going to look like? It's not going to look like the derivative.
I thought it was.
What do we use the differential equation for to get the slope field? How do we use it? What we plug in, and what do we get? We get slopes. So those are the slopes of what?
That point.
The slope at that point of what? Tangent line of what? The function above the derivative. Okay? So what is the slope field going to look like?
Like the function above?
It's going to look like the function above. That's what you guys need to realize, is that the slope field is going to look like the function above the derivative. Okay? Because if we think about sine, what do you guys remember about the graph of sine? Besides that, you should remember something else about the graph of sine and the graph of cosine. You should remember the difference between those two. Sine starts at the origin, and cosine starts at the amplitude. Okay? If I look at this right here, does it look like it is crossing the origin, or is it at an amplitude?
Crossing.
It looks like it's at an amplitude to me, and what amplitude?
1.
Because to me, it looks like we've got it looking like this, which means it would be at the negative amplitude. Okay? And why is that? Because remember, this is sine. What do I get? What is the function above sine?
That was negative.
It would be cosine. It would be negative. Well, yeah, it would be negative cosine. You're right. It would be negative cosine, and that's why it's down here at the valley. Okay, so we need to remember the slope field that I'm looking at is going to look like the function above the differential equation. Okay, that's why this right here looks like cosine instead of sine, because it looks like the function above. So keep that in mind. Now, what are some other things? Say it again.
Is D the second one then?
Is D the second one? Why?
Because I integrated x.
If you integrate x, you're going to get x squared, which is
Quadratic.
which looks like a parabola, and that one looks like a parabola. So yes, this one is D. But there's something else we talked about before we went to spring break when we were drawing our slope fields that should help us when we're matching. Anybody remember anything we talked about?
X is
Pattern.
vertical will be the same.
If it's only in x, all my vertical slopes will be the same. If it's only in y's, all my horizontals will be the same. And if neither one of those are the same, then that means it's in terms of x and y.
So B
Okay.
is the bottom right.
Maybe we'll get there. So what do I notice about this one in the top middle? What do you notice about the slopes? Which ones are the same? The vertical ones or the horizontal ones? All the vertical ones are the same, so that means it had to be in terms of x. And if you notice, the only one that's just in terms of x is D. So that's another reason why we like D. All right, what else do we notice?
Both of them on that side, on the right side, they are horizontal.
Both of them on the right side are horizontal. And what about the one on the bottom left?
Oh, it's also.
It's also horizontal, but what about the one on the bottom middle?
It's neither.
It's neither. The horizontals aren't the same, the verticals aren't the same, so which one does that have to be? It has to be E. So that has to be E. So I know these other three have to be A, B, or F. Now, what can we do? What can we notice to help us figure out which one's which?
Can you plug
You can plug in, all right, what do you want to plug in?
You could do B, like you could plug in certain ones on either three and whatever it is. If it doesn't look like that, then it's not it.
Okay. So give me something you want to plug in.
in? 0.
So you want to plug in
Like you
zero.
said, like 1, 0, you plugged in 0, that's not 0.
Okay, so this if I plugged in a y value of 0, this one does not match. Okay? What about this one? If I plugged in 1, 0, would I get 0?
Which equation?
I think she was looking at B.
Okay.
So I plugged in the point 1, 0 over here, and if I plug in the point 1, 0, it's going to give me a slope of 0. This one right here does not look like a slope of 0 at 1, 0. Because 1, 0 would be somewhere around there, and my slopes definitely are not 0. Okay, so if I plug in 1, 0 over here, does it look like my slopes could be 0? Yes, we kind of like that bottom right one. And what about this one above it? Does it look like 0 there? No, so we're going to like that one to be B. Okay. What else?
You could plug in for either A or F on the 2 remaining graphs, and you could find a spot on the graph where one's negative and on the other graph it's positive, and if it doesn't match up, whatever you plug in.
All right. So give me an example.
Well, A should always be positive. Or A will always be positive.
A, all right, very good. So A, no matter what I plug in for Y, will always be positive. So that means all my slopes need to be positive. So that means this one has to be A, and this one has to be F, because F has some negative slopes in it, correct? Okay. All right, now that's one way to do it. Here's what I'm going to recommend to you, and that way I go a little bit quicker. Okay, first thing you want to do is kind of identify your trick stuff. The trick stuff is pretty easy to recognize, so identify that. Okay, and then we want to do what we did. We want to see, are my vertical slopes the same? Are my horizontal slopes the same? Okay, just like we did. Then after that, the next thing I want to do is kind of find some zeros. Do any of my slopes have 0 slopes in them? Okay, this one looks like it kind of has a 0 slope. And where does it look like it has a 0 slope at? What y value? It looks like it has a 0 slope at 4. So if I plug 4 into any of those, these 3 right here, if I plug 4 into any of those, will I get something that's close to 0? Okay, and yes, over here, if I plug 4 in, that gives me a slope of 0. Okay, so that's why I like this one. Okay, now here's something else we want to notice. When I plug in y on this one right here, when I plug in y values that are positive, what type of slopes am I going to get? Positive slopes. When I plug in y values that are negative, what type of slopes am I going to get? Negative. So that means everything above the x-axis is going to have a positive slope, everything below the x-axis is going to have a negative slope. Okay, and that's what's happening down there on the bottom right. Everything above has a positive slope, everything below has a negative slope. Okay, and then also what Brady said was on this A, I have 1 plus y squared. I know my slopes always have to be positive, and that's another way to help. So you want to look for slopes, whether or not they're positive or negative. You want to find 0 slopes as well. Positive and negative slopes and zero slopes help you differentiate between slope fields.
How come those, like on the third graph, it just gets straight? But even though your y value,
On this one,
like yeah, like the y value
if it's getting straight like that, that just means it's getting steep.
Okay.
That means you've got a steep slope. That's what that means.
Get it?
Alright, the next one I want to go to is this one. I think it's the front of the second page. Okay, but this one's a little bit different than the first ones we were working. What's different about this one?
There's more y.
There's more besides that.
It says y.
It
To separate.
Yeah, what equations are we dealing with?
Just y.
We're dealing with the regular equations. We're not dealing with the slope fields or the differential equations.
So we have to find the derivative.
So something I might want to do is find the derivative. That could be helpful. So let's go through and find the derivatives to all these. So the first one, y equals x. What's the derivative of that?
1.
1. Number 2, y equals x squared. What's the derivative of that?
2x.
2x. Okay, number 3, derivative of e to the x. E to the x. Number 4, derivative of 1 over x squared.
Negative 2 to the negative 2x to negative 3.
Negative 2 over x cubed. Derivative of x cubed.
3x squared.
3x squared. Derivative of sine.
Cosine.
Cosine. Derivative of cosine.
Negative sine.
Derivative of the square root of x.
1 over 2 squared root of x.
Derivative of 1.
0.
And derivative of tangent.
Secant squared.
Secant squared. Now some of these, the derivative is going to be very helpful. Some of them, that's not going to be helpful at all. All right. Now what? Identify the trig. So which ones do you think look like sine and cosine?
E.
E. I would say E and B look like the ones that could be sine or cosine. Now, which one's which and why?
Sine is E. Pardon? B. Because it starts at the origin.
Which one?
E. Sine.
E.
E goes with 6.
E goes with 7.
Y.
And B is going to go with 6. Who can explain why?
Graph cosine amplitudes on the origin.
Right. If you look at all these in here, I'm dealing with a maximum where I'm crossing the y-axis. On the other one, I'm just dealing with diagonals as I'm crossing the y-axis. Okay? And sine is the one that's just going to cross, and cosine is the one that's going to have a max or a min. Okay? And remember, when I'm looking at a slope field, what is it going to resemble? The differential equation or the actual function?
The actual function.
It's going to resemble the actual function. So E looks like a cosine, so that means it's got to match up with cosine. B looks like sine, so it's got to match up with sine.
And that's the case where the derivative isn't necessary.
And that's the case where, yes, the derivative wasn't very useful to me. Okay? All right, what else?
So J is, and the derivative didn't do anything,
Right,
right?
that's what Erica was just saying. The derivative didn't really help me on those two. All right, what else?
Is J 8
Is J8.
because there can't be a negative.
Very good. Okay, so Brady notices you're not allowed to have a negative inside of a square root. The only one of those slope fields that does not have negative values is J, is J, so that means 8 has to be J. Alright, what else?
C9.
Is C9. What do you guys think?
Would 9 be in C be 1?
C is 1. And 9 is G. And to me, those two are helpful. The derivatives are helpful on those, to me. Why are the derivatives helpful? Because on 9, if y prime equals 0, that means all my slopes have to be 0, and they all have to be flat. So they all have, that tells me it has to be G. And on number 1, my derivative is 1, so that means all my slopes have to be 1. So the only thing that looks like that is C. So those are examples of where the derivative was helpful.
When do you know to use the, like, to look at the derivative or the original?
When?
That's what I asked.
Like, when do you know?
All right, if it's, well, that's kind of what we're learning here. What do we learn about the trig?
It's more of the original.
Yeah, the original, on the trig, it's the derivative is not very helpful, okay? But when the derivative is just equal to a number, it's going to be helpful, okay?
So you
If it's equal to something else, then it might not be helpful. You just need to get to where you're looking at both. So far, I've knocked out E, B, C, G, and J.
Is 4D?
4D. All right, why?
Because it's an asymptote.
It has an asymptote where?
Oh, you mean on the graph?
Yeah, where's it at?
At 0.
At 0. Okay, I will go with that.
Is 3F?
Is 3F. 3 is F. That is correct. Why, Brady?
E to the x is exponential.
E to the x is exponential, and that's the only one that looks like an exponential. Very good. All right, what else? 10 is I. Why? Because what does the graphic tangent look like?
It goes like a disco.
It's got a bunch of discos, and it also has asymptotes. So as you can see here, you can see that there's discos going on in there, okay, which tells me it looks like tangent. All right, so we're down to number 2 and we're down to number 5. You could, but I don't think it's necessary. All right, what did you say? 2 is A, and that means the other one, H, has to be 5. Why? Yeah. Number 2, y equals x squared, that's parabolic, okay, and A looks like a parabola. On 5, it's x cubed. What does x cubed remind us of? A disco, and that's what's going on in H. I've got a disco going on in H. Okay, but the main thing to keep you from getting confused is, what is the slope field going to look like? It's going to look like the original function. Okay. The differential equation, that just helps us get the slope at each spot. Okay, so you need to be able to use both. All right, let's go through one more section, and then I'll let you work on it on your own. On the very last page, on the top left. Very last page, top left. I want to look at those 4. And then I'll release you to finish it up on your own. So I want to match 15, 17, 16, and 18. What do you think?
Well, A is 18. No, it isn't.
I think D is 16
You think D is 16. Why?
because of the horizontal rows.
My horizontal slopes are all the same, and that's the only one with y in it. So I'll go with that. 16 is D. Very good.
At least
B
15.
is 15.
15 has to be B. Because all my vertical slopes are the same, and 15 is the only one that's in terms of x.
17 is A.
17 you think is A. Why?
Because if you plug in 0, 0, that's the only slope of 0 at the origin. That's what I did.
That's what you did?
Yeah. All the new problem about 0. You can't have 0 on the bottom. That'd be
Here's my next question though. This point right here would be 0, 1. So this one
C.
has to be A, and this one has to be C. Okay, here's another trick on this one. If you look at 18, what's going on 18 anytime my y value is 0?
There's
Anytime my y value is 0, what does that tell me about my slope? It's undefined. And how do we graph undefined slopes? You don't. Okay? So if I look at my y values of 0 here and my y values of 0 there, which one doesn't have a slope? The top one doesn't have a slope, so that means that one has to be 18 and C has to be 17. Okay? Here's another thing you can look at. Okay, what do you notice about these slopes right here? They're all 0. What do you notice about the x values and y values at those points?
They're the same.
They're the same. And anytime I plug in x values and y values are the same, that produces a 0 slope. So that's another thing you can look at. Okay? So when you're matching slope fields, what are some techniques we want to use?
Look for your horizontal and vertical.
Look, see if my horizontal slopes are the same, see if my vertical slopes are the same. If horizontal is the same, that means it's in terms of y. If verticals are the same, that means it's in terms of x. All right, what else?
Positive and negatives.
I want to look at positives and negative slopes. Okay.
See if you're gonna have any, the ones where it's 0 on
All right. See if I have any undefined slopes. Because if there's supposed to be an undefined slope, what's it going to look like on the slope field?
the bottom.
Yeah, there's nothing there. All right. What else?
Look for the trig.
Look for the trig. Okay. And remember that the slope field is going to look like what function?
Original.
The original function. It's going to look like the original function. It's not going to look like the derivative. It's not going to look like the differential equation. All right. Finish that up for me. You get finished, go ahead and get it checked off.
So they're gonna have